just as we computed the electric field for different geometries, for point charges and for flat planes of charge, we can do the same thing for different geometries of current. So we have this mantra that is going to say that moving charges create magnetic fields. Moving charges create magnetic fields. And depending on the geometry of those moving charges, we're going to get different values of that magnetic field. So maybe the charges are moving in a straight line, or maybe they're moving in a loop. We're going to look at a few different geometries here and use that to compute the magnetic field for those geometries. And we're going to start with a straight wire. So everything I've drawn here, the current, is drawn in white chalk. So from last time, we know that a circle with a dot in it means the current coming out of the board, and the magnetic field, we can figure out from the right-hand rule, is going around counterclockwise. Moving charges create magnetic field. So we're going to have a formula for the magnetic field that has the moving charges in it, namely the current. And in this case, the magnetic field is going to be given by mu naught, that was the constant we mentioned last time, times the current, divided by 2 pi times r, where r is the distance away from the center of the wire. Now that's for a straight wire. If I loop my wire around, I'm going to get a slightly different current, or excuse me, slightly different magnetic field. So here I have a loop of current going around, and the magnetic field is coming out through the center of it. So if I want to know the magnetic field at the center, what I can do is I can take my magnetic field and set that equal to mu naught times I, again mu naught times I for both cases. This time it's going to be divided by 2r, where r, this time it's big R as opposed to little r. Big R is the radius of that loop. So slightly different formula. We still have some constant times current over distance, but we have a 2 pi in front here. We only have a 2 here. And the distances are slightly different too. This is the distance away from the wire. This is the radius of the wire loop. Lastly, we mentioned last time that you can get bigger magnetic fields by putting by wrapping your wire in a solenoid into a helix shape. And that's what we've done here. We have a wire that curls around. And we have current going in this end and coming out this end. And magnetic field being generated in the middle. So our magnetic field, again, is going to be that magnetic constant mu naught times I. This time times n, that's the number of loops, divided by L, that's the length of the solenoid. So that's this length right here. So if you have more loops, more turns per unit length, you're going to get a bigger magnetic field. And I should mention that this is the magnetic field inside the solenoid. Outside the solenoid, the magnetic field is going to be fairly small, but inside, you can see that the magnetic fields from all of those wires, if you do the right-hand rule, magnetic field is all going to combine constructively so that you're going to get a big magnetic field on the inside, whereas they're going to cancel out on the outside. So those are our 3 geometries. We have a straight wire, a single loop of wire, and a solenoid. You should be able to calculate the magnetic field for each of those 3 geometries. So we have here an oscilloscope. And an oscilloscope is essentially a cathode ray tube. And what that means is there's a long tube inside my little box here that fires electrons at this fluorescent screen. And we can see where the electrons are hitting the screen because there's a little dot in the middle here. And as I adjust the position of the dot, what I'm doing is I'm changing and deflecting the electron beam so that I can make the electron beam go up or I can make it go down. And if we connect different voltages to our oscilloscope, we can measure the voltages by basically how far this electron beam gets deflected. Now I also have here a little bar magnet, and we're going to use the bar magnet and see what happens when I bring the bar magnet over the cathode ray tube. So we're going to start with the north pole of my bar magnet. I'm just going to bring it down onto the top
And you can see, look what's happening to my electron beam there. Let me just center it really quick. It should be right in the middle there. And as I bring my bar magnet down from the north pole, we can see that the electron is getting deflected off to the left. Let's see what happens if I do the same thing with my south pole. So the blue end is the south pole. And you can see my electron beam is getting deflected now to the right. So it's clear that the magnet has some property where it can deflect my electron beam. In fact, if I just wiggle it around here, you can see I'm deflecting that electron beam. Now this is kind of curious because the electron beam or static charges did not get deflected at all when we just brought a magnet near a set of static charges. But now that the charges are moving, I can exert a force on them using my magnet.
Let's see if we can make sense of how magnetic forces work using a few simple examples. And to do this, we have a new mantra for magnetism. Our mantra for magnetism is going to be this. It's very similar to our mantra for electrostatics, but slightly different, and the way we're going to apply it is going to be very different. So our mantra is going to be this. Mantra one, moving charges create magnetic fields B. Okay, so moving charges create magnetic field. Part 2, magnetic fields B create forces on other moving charges. So magnetic fields create forces on other moving charges. Okay. This seems simple, but it gets a little bit complicated in practice. So let's go over here. Here I have a positive charge, and I have a velocity vector v, so the positive charge is moving to the right, and we have a magnetic field that's pointing up. So what direction is the force on that moving charge going to be? Well, it turns out this is the screwy part. The force, which I'll call F, on this charge is going to point out of the page. Or out of the board, I should say. So I have 3 vectors here. I've got my velocity vector pointing this way. I've got my magnetic field pointing up, and I've got a force pointing out. So that's 3 vectors, they're all perpendicular to each other. How does that work? How can we visualize this? We're going to have to be working in 3 dimensions. And to visualize how this force works, again, we're going to have to take advantage of the right-hand rule. Now, this is a little bit of a different right-hand rule from the one we use to find the direction of the magnetic field. But much like the first right-hand rule, it's still going to involve your right hand. So here we go. The way you figure out the direction of the force is as follows. You're going to take your fingers, point them in the direction of the velocity. Right now my fingers are going this way. And I want to hold my hand in such a way that I can curl my fingers, not my thumb, but the rest of my fingers, in the direction of the magnetic field. So if I hold my hand this way, I curl my fingers down, and that's not the direction the magnetic field points. So I have to twist my hand this way so that my palm is facing up. And when I do that, then, only then, can I point my fingers, curl my fingers in the direction of the magnetic field. So you start with your fingers in the direction of the velocity, orient your hand so that you can curl them to the magnetic field, then your thumb will point in the direction of the force. In this case, my thumb is pointing out. So it's more of a complicated procedure for figuring out the direction of the force. But it does work. This is really the simplest way that we can use to figure out the direction of the magnetic force.
So let's see if we can figure out why the electron beam gets deflected one way when I put it near a north pole, and the other way when I put it near the south pole. We have electrons traveling toward our camera, so they're coming out towards you and hitting this screen. And if we use our right-hand rule, we know that if the electrons are coming towards you, and I put my fingers in the direction of the velocity, and now the magnetic field is pointing down. We would use our right-hand rule. This is going to be a little bit hard to do on camera, but electrons coming towards you curl toward down, so the force is in the direction of my thumb, which would mean the force is to the left, except that or to the right rather, except that they are negatively charged, so that flips the direction so that the force is to the left. So when I do that, you can see my electron beam gets deflected to the left. When it's in the opposite direction, so again, charges are moving toward you, but now the magnetic field is pointing up, so I've got to curl my fingers the other way. My thumb points to the left, but it's negative, so I have to flip that direction, so the force is pointing to the right. Well, if I do that, you can see when I bring the south pole of my magnet towards the oscilloscope, the electrons get deflected to the right, just as they should according to the right-hand rule.
So let's go through that one more time. This is the right-hand rule for forces. And mathematically, we can write it out as F equals QV cross B. Now, the cross here is known as the vector cross product. This is not the same thing as just multiplying. Because the vector cross product will actually give you a vector when you're done, which is what we need. Right? We need a force vector. So I need to know what direction my force points. So I need a vector at the end. So we would say that this is QV cross B. I'll get to how to calculate that in a moment. But let's just figure out how the direction works. Starting off, it's QV cross B. So we want to point our fingers in the direction of B. Of V, I should say. Point fingers in the direction of V. Okay. Point fingers in the direction of V. Next, curl your fingers to B, the magnetic field. Point fingers in the direction of V, got to curl them to B. I can't do that this way, I've got to hold them like this. And my fingers can curl from V and point up to B. And curl my fingers to B. When I do that, your thumb points in the direction of F. V to B, thumb points in the direction of F. Let's try that. Let's try another example of that. Let's see, let's fix this. Let's say you have a magnetic field that's coming out of the board, and you have a velocity that's pointing up. What direction would the force point? Again, let's say there's a positive charge here. Let's see, velocity is pointing up, point fingers in the direction of V, curl them in the direction of the magnetic field. The magnetic field is out of the board, so the force has to point this way. Start along V, take V, cross B, force is in this direction. Okay, good so far? Good. Let's do another example. Oh, what's a good random direction? Say your velocity is this way. And your magnetic field, say your magnetic field is also this way. And again, it's a positive charge. What happens in this case? Well, V and B are pointing in the same direction, so I can't really curl, like if they're both up, I can't curl to up. So how do I figure out the direction of the force? Well, it turns out in this case, if the velocity and the magnetic field are in the same direction, your force is going to be 0. There is no force if velocity and magnetic field are pointing in the same direction. The same thing is true if the velocity and the field are pointing in opposite directions of each other. So if my particle is moving down and the magnetic field points up, well, I would point my fingers down, and then to go up, I could curl this way, which would give me a force pointing in, or I could curl around the other way, which would give me a force pointing out, or I could curl this way, which would give me a force pointing this way. It's undefined. The only answer we can say for this is that the force is going to be 0. Let's try another one. Okay, so that was for if V and B pointed in the same directions as each other. Let's try a slightly different angle. V points up and to the right, B points this way, and there's some angle theta between them. Again, we'll do a positive charge. Let's say, point fingers along V, curl them to B, you'd have to go this way, so the force is again pointing out. Force is out of the board. Let's do another one. Let's try a negative charge this time. We've got a negative charge. It's moving in this direction, moving to the right. Let's say it's got a magnetic field, running out of green here. Magnetic field pointing up. Which direction is that going to feel a force? Well, if I look here, it's going to, again, it's just V cross B. So I would say V cross B, my thumb points out. That gets me the vector cross product. V cross B points out. But I have a negative charge in here. So my force would be pointing out, but that negative is going to flip it. So that your force now points into the board. So the force flips direction for negative charges. The only reason it does that is because we have this Q in the force equation. So when you multiply a negative times a vector, it flips the direction of the vector. So a negative charge will just flip the direction of that force. We've talked about how to find the direction of the magnetic force. So again, our mantra, going back to the beginning, moving charges create magnetic fields. And then those magnetic fields create forces on other moving charges. We're trying to figure out the magnitude and direction of that force. We've talked about finding the direction. So you just take V cross B, that will give you your direction. But how do we actually compute the magnitude of that force? Well, I've told you that this is a vector cross product. So we're taking V cross B. And in general, whenever you do a cross product in physics or math or wherever you happen to be doing a cross product, suppose you have two vectors, A and B. The cross product works as follows. If you take A cross B, then the magnitude of that result is equal to the magnitude of A times the magnitude of B times sine theta, where the theta is the angle between the two vectors. Okay. We talked about if the vectors point along each other, then the cross product is 0. So if V and B point together, that theta is 0, so you're going to get the sine of 0, which is 0. Okay. This is just the definition of the cross product. So a helpful way to remember this is, what do you get if you cross an elephant and a giraffe? So what do you get if you cross an elephant and a giraffe? Elephant, giraffe, sine theta. Okay. That should help you remember it. But here, we're taking V cross B. So that will be F is QV cross B. But that would just be, if all we want is the magnitude, so the size, We're not concerned with the direction. That'll be QVB times the sine of the angle between them. So we need to know three things. The charge that's moving, the speed that it's moving with, the magnetic field that it's moving through, magnitude of the magnetic field, and the angle between the vectors V and B. So charge, velocity, magnetic field, and the angle between the two. We've got another setup here. This is similar to the setup we had before, where we have current coming through my wire, heading to the right, back up here, and then back through to a power source. So we have current going down, around, back up through here, starts at the red wire, down, around, back through here, and then goes back through that black wire that you can see connected to the leads above. So what we're going to do here is we're going to pass some current through our wire, and we're going to see what happens when it's in the presence of this magnetic field. So right here, these two blocks right here are actually a magnet. We can tell they're a magnet because if I bring a paper clip close to them, the paper clip will stick. And if I take the paper clip away, it's actually a pretty strong magnet, so it's got to pull with quite a bit of force to get that paper clip off. So I'm going to do two things. First of all, let me take my magnet out of the way. And I'm just going to leave my wire sitting there. And I'm going to turn on the power source that I have just off to the side over here. And I'm going to turn that up, and we're going to pump 3 amps of current into that wire, that little wire, the swing-shaped wire. And we're just over 3 amps, we're at about 3.1 amps, and you can see nothing particularly interesting is happening to the wire. It's just current pumping through without a whole lot happening. Now let me turn that current off. Now we're going to see what happens when I put it in the presence of a magnetic field. So again, we've got, right now the current's off. I'm going to turn it on in just a sec, but current's going to be pumping down, around to the right and back up. And you can see, let me just stop that to begin with. As I turn the current on, almost instantaneously, that wire gets drawn into the magnetic field. If I turn the current off, the magnet goes away, or the wire goes away. As I turn the current on, the wire gets attracted again. Current on, current off. Current on, current off. So why is the current carrying wire attracted to the magnet? So point charge again feels a force of QV cross B, which is equal to QVB sine theta. However, normally in our everyday lives, most of the charges that we see moving are in a wire. So what happens if we have a current carrying wire? So suppose here's a wire. We've got some current I traveling down the wire to the right. As before, we've got some magnetic field that's pointing at an angle theta relative to that current. How would we compute the force on the wire? Well, the force on the wire is again going to depend on the current and how fast those individual charges are moving, but the current's going to take care of that. So instead we're going to multiply by the length of the wire. So the wire has some length L times the magnetic field. And again, since it's really a cross product, it depends on the sine of that angle. So it'll be the current times the length of the wire. A longer wire will have more force because there's more charges that are moving inside. Times the magnetic field times the sine of the angle. Very similar to this formula, except instead of QV, you have the current times L. So it turns out you can do pretty neat things with the magnetic force
even if you only have a few things around the house like paper clips, pins, and a battery. So what we have here, what I've done, is I've taken two paper clips, and these two paper clips have been folded in such a way that I'm just going to use these like a stand. And I've pinned them down with two metallic pins and connected a power source to them. So we've got a red lead, which is going to be the positive end of the battery, and the black lead, which is going to be the negative end. So that current is going to flow from this paper clip to this paper clip. And it's going to flow through this little piece of copper wire, which has been twisted into just a ring with a few loops. And I'm just going to put the copper wire in there. It'll balance pretty nicely. Let's just stop it there for a sec. It'll balance pretty nicely there, and it'll pretty much just sit there with current flowing through it if I don't do anything else. But I am going to do something else because I also have this fairly strong magnet, and you can see is if I put the magnet near the copper wire, all of a sudden I can exert a force on it. And you can see that's a pretty strong force that we can get that to move with. And if I get it close enough, come on, I can get that wire to twist. And this is basically, and it'll keep turning forever, provided that it maintains electrical contact. I do have to keep it in the middle. But this is the principle behind an electric motor. Now, if I want that to keep going, all I have to do, you can see a little bit of sparking there, all I have to do is just leave my magnet there. Occasionally it'll get a little stuck. But this is the principle behind an electric motor. All we're doing is we're creating a magnetic force because there's current moving in one direction around the wire, and as it interacts with the magnetic field, that will create a force. The force will create a torque that will cause this wire to twist, and as it twists around, it's constantly getting a new force that's pushing it and renewing the twist.
That wire to twist. This is basic.